Everyone, welcome to the 12th session of Electromagnetic Theory and Interference course. In this session, let us learn about electric flux and electric flux density. So, electric flux was discovered by Michael Faraday, where he was doing an experiment on electric field. He showed that the electric field around a charge, it is imagined to be like lines of force around it. Okay, so the total number of lines of force in any electric field is called electric flux. The total number of lines of force in a particular electric field is called electric flux. And this was represented by the symbol psi. And similar to the charge, the unit of electric flux also is coulomb. Okay. We just now saw that electric flux is nothing but lines of force around the charge. So these lines of force are called flux, right? So the flux lines start from positive charge and terminate at negative charge. So in the absence of negative charge, flux lines will emerge from the positive charge and terminate at infinity. Whereas if the positive charge is absent, flux lines comes from the infinity, okay, and terminate on the negative charge. And wherever there are more number of lines of there is more number of flux lines, we can understand that the electric field is stronger. And always the flux lines are parallel. These lines are parallel and never cross each other, and they are also independent of the medium in which the charges are placed. Okay. The flux lines can enter or leave the charge surface normally only, perpendicular to the surface only. The charge flux lines will enter and leave. If the charge on a body, okay, is plus or minus q coulombs, then total number of lines originating or terminating on it is also q. Charge on a body is plus or minus q coulombs. Total number of lines originating and terminating, that is also q. So we just now saw that total number of lines is nothing but flux. That electric flux is equal to the charge present. Okay, the charge in coulombs. So if the charges is large, then the flux is also more around the surrounding that particular charge. I can always say electric flux as a displacement flux. Okay, and it is a scalar field only. It's not a vector, it is a scalar field. Now we define one term called electric flux density, which is going to be a vector field associated with that particular flux. Okay, that electric flux density we are going to see now. So to understand it, so we already know the flux lines are starting from positive charge and terminating at negative, right? We consider a unit surface area. To that surface area, how the flux lines are originating and terminating. Okay, so number of flux lines crossing per unit surface area is termed as, so this is one, number of flux lines crossing per unit surface area is termed as electric flux density. This is represented by a vector, D vector symbol. Okay. Always the net flux passes normal to the unit surface, right? And this denoted by D vector, as I mentioned earlier. This is it has a specific direction. If you see the D vector, it has a specific direction, and it is normal to the unit surface that we have considered, and it is along the flux lines. Okay, and it is along the flux lines. So how can I denote the unit of this electric flux density? Since the flux has a unit of charge and surface area by meter square, I can define by coulomb per meter square. So this electric flux density is otherwise called as displacement flux density or displacement density. Hence it is denoted by letter. Let us understand about the vector form of electric flux density. So for that we consider a differential surface area ds, and at a point P we are interested in finding the electric flux density D vector. So the flux crossing this differential area is d psi. The direction of d, if you see, it is same along the direction of flux lines, and it is also same, okay, as that of the unit vector, okay, that is normal to the differential surface area, and the d vector also is normal to the surface area, right? And we can write the relation, since the electric flux density is nothing but the flux lines crossing the surface area is d psi by ds, and the corresponding unit vector normal to the surface a n cap. The unit is coulomb per meter square. D psi is the total flux that is crossing normal to the differential area ds, and an vector is the unit vector that is having the direction which is normal to the differential surface area. Okay, let us see in the next session. Thank you everyone.